Write down the letter that represents each of the following. That is 2.1. And 2.1.1, we are looking for the letter that represents an alcohol. So let's go ahead and take a look at the options that we have. A is clear to see because we have the structures, right? And then C is also clear to see what is happening because we have the actual name. Same is true with D. Even though we don't have the actual name, we have the molecular formula, we can sort of work out what is happening. But there's an issue here with E, F, and H. It's really confusing to see what is happening when they are written like that. So it's better, before we even answer any question, we actually draw those structures so that we can see what is happening, and then it is going to help us as we answer our questions, I'm assuming. So let's go ahead and do that. First of all, let's start with E, right? So E, we have CH3, so we're going to have a carbon and 3 hydrogens, followed by, okay, we have a carbon there, and then in brackets we have CH3. Because it says CH3, it obviously has to be a branch, because it cannot be a carbon that is bonded to other carbons and has 3 hydrogens bonded to itself also. It is actually impossible. So we have a carbon that acts as a branch, and then it's actually 2 and not 1 because of these 2 outside there. So that is that part. And then as we proceed, we have a carbon followed by 3 carbons, right? So let's say 1, 2, and then the third carbon has 3 hydrogens. So that is 1, 2, 3. But as we look at these 2 carbons, we need 4 bonds, right? Because we know that a hydrogen is not a hydrogen but a carbon. It's supposed to accommodate 4 bonds. So let's see how that can be true. There's no other hydrogen left, so clearly there has to be multiple bonds between these carbons, right? So they all have 1, 2 bonds, right? So in order for it to be 4, this will be the third one, and this will be the fourth. So this is the molecular formula of compound E. Let's do the same for compound F and H. Right, so let me just erase 2.1.1 here and draw F and H. So F, we start with CH3, so that is C and then H3, right? And then we are followed by a carbon bonded to 2 oxygens. So obviously we know what is happening here. We're going to have 1 oxygen bonded to the carbon like that, and then another oxygen in that fission. Here we have an ester, it seems like. And then we have CH2 with 2 on the outside. So what does that mean? C, 2 hydrogens, another carbon, 2 hydrogens. If it was CH3, it was going to be a branch, because it is impossible to have CH2 to have CH3 as a carbon in the longest carbon chain. It has to be a branch. So there we go. That is CH2 and with that 2 on the outside. And lastly, we have this carbon with 3 hydrogens. That is F. So we have E, F, and lastly, let's do H. It seems like a painful exercise, but it is really important for us to do this, right? More especially when we have these kind of formulas that we usually don't see. So H, a carbon with 3 hydrogens. So there we go. And then we have a carbon, and then we have CH3 with the 2 on the outside. So those have to be branches because they cannot be in our longest chain. So 1 carbon, 3 hydrogens, 1 carbon, 3 hydrogens, and then followed by a carbon, 1, 2 hydrogens, carbon, 1, 2, 3. So that is E, F, and H. It is going to be easy for us to see what is happening as we move forward. So back to the question. 2.1.1, we are looking for an alcohol. So A is clearly not an alcohol, B is not an alcohol, C is not an alcohol, but D can be an alcohol. Let's take a look at it and see if it makes sense. For D, we have C4H10 oxygen, right? So what is the molecular formula? Not the molecular formula, but the general formula rather of alcohol. We have CnH 2n plus 1 OH. So let's see how many hydrogens we're going to have if we have 4 carbons. So if we have C4, we're going to have 2 multiplied by 4 plus 1, that is 9 OH. Clearly this is C4H10 oxygen. So the answer to 2.1.1 is D. it's easy to see now that that is actually an alcohol. And then a 2.1.2, a compound with a 4-methyl group. So ketone, right, is carbonyl. It's carbonyl group, right? And then aldehyde is 4-methyl. So we are looking for aldehyde here. Which letter represents an aldehyde? It's easy to see that it is A there, because we have the carbon double bonded to the oxygen at the end of the chain. So 2.1.2, we have A as our answer. What about 2.1.3? An unsaturated compound. Unsaturated, we have multiple bonds, right? And then look at E, F, and H. Should be easy to see here that the answer is actually E, right? It's easy to see now because we actually have the structure. You can see the multiple bonds causing it to be unsaturated. If we didn't draw it out, it was gonna be a bit difficult for us to see. But then because we actually have the structure, it becomes a little bit more simple. So this is E, and let's do 2.2. So 2.2.1, we're looking for the IUPAC name of compound B. Right, so first things first, we need the longest carbon chain, right? So let's see, 1, 2, 3, 4, 5, 6. If we go down, we're gonna have 1, 2, 3, 4, 5. So clearly going up, that's where we have our longest chain. So let me just circle these. Let me just circle this so that we can have a bit of clarity. This is our longest carbon chain. So now we need to decide where we are going to start numbering. Do we start numbering from the top, or do we start numbering from the bottom? Let's see what is happening. If we start numbering from the right, we're going to have 2 branches on the third carbon, right? We're going to have 1, 2. We're going to have those 2 branches on the third carbon. But if we start numbering from the top, we're going to have these 2 branches on the third carbon, right? So here, because we are faced with this case, we are going to use alphabetical order, because whether we start from the left or we start from, whether we start from the right or we start from the top, we're going to end up reaching our branch at the third carbon, and both those branches we actually have 2, right? So here the priority will be alphabetical order. Okay, so bromo comes before methyl, right? So we must start with bromo, therefore. So this is gonna be 1, 2, 3, 4, 5, 6. So we have those branches, bromo on the third carbon. So 3.3 dash dibromo dash. So the methyl, it's on the 4th carbon, right? So 4.4 dash dimethylhexane, because like we said, we have 6 carbons on the longest chain. So hexane. So there we go. That is the IUPAC name of compound B. And then the IUPAC name of compound E. Compound E, we have the structure up here. So let me just see if I can actually drag this structure. Okay, I thought it was not working the way I wanted to. Come on, let's go down. Okay, let me just copy it and see if I can maybe paste it here. Okay, there we go. So this is the structure of compound E. Obviously here we have a functional group, right? So we have to start numbering our carbons from the side closest to the functional group. So this is going to be the first carbon, second, third, fourth, fifth, right? This is our longest carbon chain. Even if we go up, we're going to end up having 5 carbons on our longest chain. So that is pent 2YNE. Okay, we know that for sure, pent 2YNE. And then we have branches on the 4th carbon. So we're going to have 4.4 dash dimethyl pent 2YNE. Right, so there we go. That is the IUPAC name of compound E. 4.4 dimethyl 2YNE. Okay, I'm happy with that. Let's go to 2.3. So in 2.3, we're supposed to define the term functional isomer, right? So organic compounds with the same molecular formula, but a different functional group. And then 2.3.2, write down the letters that represent these functional isomers. So in our context, in our curriculum, we only have two pairs of functional isomers. We have ketone, aldehyde, right? And then we have carboxylic acids and esters, right? These are the two pairs that we have which can work as functional isomers. So let's go back to our table and see what we can cook here. So compound A is an aldehyde, right? So if we have a functional isomer of that compound A, it should be a ketone with 4 carbons, right? As you can see, compound C is butanone. That is a ketone. So the answer to 2.3.2, we have A and C. Let's just verify that the question said letters. Okay, so letters that represent these functional isomers. So there we go. A and C are functional isomers. Let's move to 2.4. So 2.4.1. Compound F is formed when a carboxylic acid reacts with another organic compound X. So compound F, we have drawn compound F. So let's just copy it because we're gonna need it there. Copy, and then let's see if we can paste that. Okay. Can I paste? Maybe some difficulties here. Okay, there we go. That is compound F, right? I don't know what that is. Let me. Okay, this is just a mess. Is this compound F? Okay, this is compound F. Let's just carry on with compound F like that. So that is compound F. So compound F is formed when a carboxylic acid reacts with another organic compound X. Oh, X is not here on the table, it's just an unknown organic compound, right? So 2.4.1, name or formula of catalyst used. Obviously H2SO4, right? Or sulfuric acid, because this is an ester. If it is formed from a carboxylic acid, it has to be reacting with alcohol. And then 2.4.2, in the presence of sulfuric acid. A type of reaction, esterification. Esterification. Yeah, other people will say condensation, which is, I've seen in previous memos, should be fine, but it's esterification. Okay, 2.4.3, structural formula of compound F. So compound F is the carboxylic acid that is used, right? Compound F is the carboxylic acid that is used. Oh no, compound F is actually these which we have here, which we have drawn. So just to be more clean with my presentation, we just need to add hydrogens everywhere else. We have the answer to the question, really. So there we go. That is compound F. And then 2.4.4, IUPAC name of compound X. So carboxylic acid reacts with a compound X. So the compound X must be the alcohol. So let me put a line here, right? So not there, but here rather. So this part should come from the alcohol, and then this part should come from the acid. So the alcohol has 3 carbons. So what should be the IUPAC name of that alcohol? Let me know in the comments. Here we go. Define the term vapor pressure. That's what I'm actually telling you. I'm telling you to define the term vapor pressure. That is 3.1. Let's take a look at 3.2. So write down the vapor pressure of compound C. Let's go through the question statement and see what is actually happening. So the vapor pressure of different organic compounds are determined at 20 degrees Celsius. The vapor pressures of compounds A, B, and C are not shown in the table, as we can clearly see that we don't have here. And then 3.2 says the vapor pressures of compounds A, B, and C are given in the random order below. Okay, And then 3.2.1, write down the vapor pressure of compound C. So how are we supposed to know which vapor pressures for compound C, so on and so on? Let's go through our table. So we have A, B, C. A is pentane, B is 2-methylbutane, C is 2.2 dimethyl propane. So these three organic compounds, they have the same molecular formula, hence they have the same molecular mass. But how do they differ? Let me show you. So compound A is pentane, so we have 1, 2, 3, 4, 5. I'm not including the hydrogens because that doesn't really affect where I'm going with this. And then compound B is 2-methylbutane, so that is 1, 2, 3, 4, and then we have a branch there. Compound C is 2.2 dimethyl propane, so that is 1, 2, 3, 1, 2. So which one of these vapor pressures can we relate to compound C? The highest vapor pressure. The answer to 3.2.1 should be 146 kilopascals. That is 3.2.1. 3.2.2, we are supposed to explain why we are saying that, and that is for 3 marks, right? So take a look at A, B, and C. How do these three compounds differ? They differ in the degree of branching, right? So the first point that I would make is that compound C is more branched. It's more branched, right? Compared to A and B. I think there's an alternative to saying this, which is it is more spherical. That is probably going to be another option that you will find on the memo. So compound C is more branched compared to A and B. Okay, so that is the first point. What point can we make after that? We have said that compound C is more branched compared to A and B. What else can we say? What is the consequence of being more branched? That is the question really. It has the more branched a compound is, the less surface area it has, right? That is the second point we can state. And then if it has less surface area, it has less intermolecular forces, right? Well, let me not say less. That is not the right way of phrasing it. It has weaker intermolecular forces. Weaker intermolecular forces compared to B and A, right? And then weaker intermolecular forces means a lower or low boiling point, melting point, but higher vapor pressure. So the highest vapor pressure between A, B, and C should be that of compound C because of those reasons. That is 3.2.2. So there's different ways you can phrase these points, right? But your answer should be along those lines, right? It is more spherical, so it has weaker intermolecular forces. Less energy is going to be actually required to overcome the intermolecular forces in compound C, as it has a lower melting point, melting point, but higher vapor pressure. 3.3.1, compound D and E are compared. So D is propanoic acid and E is butanol. So already we expect propanoic acid to have the lower vapor pressure, right? Because it has stronger intermolecular forces. But let's hear the stories. Which compound has the lower boiling point? So we are given the vapor pressures as it is. The vapor pressure of propanoic acid is 0.32 and that of butanol is 12.2. So which compound has the lower boiling point? Butanol, right? The lower the boiling point, the higher the vapor pressure. The higher the boiling point, the lower the vapor pressure. That's how it works. And then 3.3.2 fully explain the difference in vapor pressures between compounds D and C. Okay, so obviously we will have to talk about the functional group in these two compounds, the intermolecular forces that you find. So propanoic acid possesses or has hydrogen bonding, right? Two sides of hydrogen bonding to be specific, right? Hydrogen bonding. While butanol, so it is an aldehyde, has dipole. Yeah, aldehydes have dipole forces, right? And then the intermolecular forces in propanoic acid should be stronger than that in butanol, right? Hydrogen bonding is stronger than the dipole forces. As a consequence, more energy is required to overcome the intermolecular forces in compound D, which is our propanoic acid, right? More energy is required to overcome the intermolecular forces in compound D, and as a consequence, it is going to have a higher boiling point, melting point, but lower vapor pressure, right? So in 3.3.1, the answer should be E, because E has the higher vapor pressure. If it has the higher vapor pressure, it's going to have the lower boiling point, because if a compound has the higher boiling point, it has the lower vapor pressure. So you can phrase your answer in terms of D, you can phrase your answer in terms of E. Both should be fine, right? In E, you'll be saying, oh, it has a weaker intermolecular forces, and then in D, you'll be saying that it has stronger intermolecular forces. That is question 3. I think it was quite doable. Which question do you want me to do next? We can go to question 6, if you insist. Or we can go to question 7, more especially the last one. Let me know in the comments. Here we go. Define the term cracking reaction. That's me. I'm telling you, I'm not reading the question. Define the term cracking reaction. 4.1. Let's take a look at 4.2. Is the product in reaction 2 a primary, secondary, or tertiary haloalkane? Give a reason for the answer. Let's go through the question statement and see what is happening. So reaction 1 is a cracking reaction, forming 2 organic compounds, W and T, as the only products. Okay, right. And then this is compound, this is a reaction 1, and then W and T are the products of the cracking reaction. Back to our question. In the production reaction, is the production reaction 2 a primary, secondary, or tertiary haloalkane? So let's go ahead and see that. So this is reaction 2, right? We can see the product in reaction 2 here. We are given the condensed structural formula. So if we just draw that in full, it should be easy to see that we have C, carbon, 1, 2, 3, followed by a carbon, 2 hydrogens, followed by another carbon with 2 hydrogens. And then the last carbon has 1, 2 hydrogens and Br, bromo, right? So this is clearly a primary haloalkane. This is clearly a primary haloalkane. So the answer here to 4.2, it is primary haloalkane. It is a primary haloalkane. And then we're supposed to give a reason for the answer. It is a primary haloalkane because the carbon bonded to the halogen is bonded to only one other carbon, right? One other carbon. Okay, so that means that it is a primary haloalkane because this carbon, which is bonded to the halogen, is bonded only to one other carbon. So that makes it primary. So if we had that Br there, okay, it will be a secondary because it is bonded to 2 other carbons. And then if we have that Br there at the top and we have a branch here, then it will be a tertiary because it will be bonded to 1, 2, 3. But in our case, we just have a primary haloalkane. The carbon bonded to the halogen is bonded to one other halogen. That is 4.2. 4.3.1, we are looking for the structural formula of compound W for 3 marks, right? So we are talking about cracking here. That is reaction 1. In our context, we only talk about cracking of alkanes. We only talk about cracking of alkanes. So we know that compound U is an alkane, right? And then take a look at this. After cracking, we have compound W, which is what we are essentially looking for here. And then we have the compound T, of which we have C4H8, right? And then from compound W via reaction 2, we end up with a haloalkane with how many carbons? 1, 2, 3, 4. So we know that compound W has 4 carbons. So we have C4. But how many hydrogens does it have? Let's take a look. We are seeing that compound U, of which these two products originate from, it is an alkane. It is an alkane. Let's keep that in mind. And then of this alkane, it has 8 carbons. An alkane has 8 carbons. So how many hydrogens does it have? It has H2N plus 2. N is 8, as you can clearly see. 2 multiplied by 8, that is 16. Plus 2, we get 18. So we have 18 hydrogens in total. We have 8 here. So here we need 10 hydrogens. So there we go. This is actually compound W. Compound W is butane, right? So the question, what does it say? Structural formula of compound W. So not the molecular formula, but actually the structural formula. So you need to deduce what compound W is, but then on top of that, actually draw the structural formula. So the structural formula of butane, so we have a carbon, 3 hydrogens, carbon, 2 hydrogens, another carbon with 2 hydrogens, and the last carbon with 3 hydrogens. So this is 1, 2, 3, 4. That is compound W. Okay, so that is 4.3.1. Let's take a look at 4.3.2. Molecular formula of compound U. So let's go ahead and take a look at compound U. Where's compound U? Oh, compound U is the organic compound that you're studying with. Should be an obvious answer if you get 4.3.1 right. So it should be impossible to get 4.3.2 wrong if you got 4.3.1 right, because how else are you supposed to get 4.3.2 without getting 4.3.1 right? But anyway, stories. 4.3.2, we said that it is C8H18. What does the question say? Molecular formula, right? So we can write it like that and leave it like that because the question is looking for the molecular formula. And then 4.4.1. Here we had to really think, right? We had to really think about this one. Let me show you why I'm saying that. Okay, so the name or formula of the inorganic reactant of reaction 2. We said that compound W is C4H10, right? So we have, let me just write that nicely. C4H10. That is compound W. So compound W is an alkene, right? It is an alkene. Not an alkene, but an alkene. I'm sorry for that. Just a mistake. It's an alkene. And then we add something, and the product is a haloalkane. The product is a haloalkane. So clearly this is a substitution reaction. This is a substitution reaction that we have in front of us. But then how does that help us with the question? Let's read the question once more. The name or formula of the inorganic reactant that is needed. In our product, we have bromo, as we can clearly see here. So the inorganic reactant that we need for this reaction is actually Br2, right? So the question says the name or formula. So let's just write the formula. We can forget about everything else. That is the inorganic reactant that we need. And then 4.4.2, the type of reaction. Well, how do you get 4.4.1 right and get 4.4.2 wrong, right? The type of reaction that takes place here is substitution. Substitution. Yeah, why do we say so? we start with a saturated organic compound and we end up with a saturated organic compound. Something has been substituted, nothing has been added or removed. 4.4.2. And then last question, is it? No, it's not. It's just the last question on this page. 4.4.3, we're looking for one reaction condition. So I'm going to leave this one for you. We have reaction 2 here. What is the reaction condition? Let me know in the comments. Right. And then what I like about this question paper is that we don't actually have to go up to see the diagram. The diagram is given again in the next page. Right. This is really helpful. Okay. 4.5, name the type of elimination reaction. Name the type of elimination in reaction 3. So we're told that reaction 3 is an elimination reaction. But how are we gonna figure out which elimination reaction it is? Well, a haloalkane as the main organic compound that you're studying with can only lead to one elimination reaction. If you start with a haloalkane, there's only one possible elimination reaction. So we don't need any other information in order for us to answer this question. The mere fact that we start with a haloalkane, it tells us which elimination reaction it is. This is dehydrohalogenation. So 4.5, dehydrohalogenation. Right. It cannot be anything else. That is the only option we have. And then compounds R and T are positional isomers. So let's take a look at compounds R and T. So R and T are positional isomers. So what is compound R? So compound R should be a alkene, right? We know that because we're being told that it is a positional isomer of compound T. Apart from that, it is a result of an elimination reaction. It will always be an alkene. Okay, so we are told that compound R is an alkene. But what are we supposed to do with that? I don't know. We'll figure it out. So here, let's just have alkene. We have an alkene. So alkenes can only undergo one type of reaction, addition reaction. There's nothing else you can do to an alkene except from adding. So this is an addition reaction, right? Let's see how that will help us with the actual questions, really. The inorganic reagents shown below are available for reactions IVF, so for reaction 4 and reaction 5. And then we have those inorganic reagents that are given. And then 4.6.1, the balance equation for reaction 4. Or write down the balance reaction for reaction 4 using structural formula and the correct inorganic reagent shown above. So let's try and crack the equation. Okay. So we need the complete reaction for reaction 4. We need to figure out what that is. Okay, it's fine. We already know that reaction 4 is an addition reaction. So what is reaction 5? So if it is an addition reaction, right, it means that here we end up with a saturated compound. Here we have a saturated compound. And then here, organic compound T, it is unsaturated, right? Unsaturated. So reaction 5 is elimination. Elimination. If we start with a saturated and we end up with an unsaturated compound, it is elimination. Something has been eliminated. Okay, so it is important for us to figure that out, that reaction 4 is addition and reaction 5 is elimination. So what can we possibly be adding in reaction 4 and what can we be eliminating in reaction 5? Okay, let's play around with the different options we have. So this is BR2. This is BR2. So if we add BR2 in reaction 4, we end up with a haloalkane, right, with 2 bromo, right, with 2 Br in the chain as branches, right? So how can we get rid of 2 Br in the branches? Well, H2SO4 is not going to work. NaOH is not going to work. HBr is obviously not going to work. H2 is not going to work. So if we add the Br2 there, we're going to have issues in that we cannot remove it with any of the other reagents. So Br2 is not playing a part here. It cannot help us. H2SO4, we should not be even thinking about H2SO4, right? I would be thinking about H2SO4 if we had a esterification of some sort, of which it will just be a catalyst either way. So I'm not even thinking about H2SO4, right? At this point, I'm not thinking about H2SO4, right? And I'm not thinking about Br2. But what happens is that if I add HBr, okay, if I add HBr, I'm gonna end up with, let's say, 1, 2, 3, 4, and then I have Br somewhere there. So this will be compound S if I add HBr. But can I remove H and Br to end up with compound T with any of the other reagents that we have in the table? Yes, we can. And AOH, right? Because it is concentrated, so it can be an elimination reaction. So we need HBr here in reaction 4. And then here in reaction 5, we need NaOH. That would totally be fine. That would work. So the balance equation for reaction 4 using structural formula. So compound R, we have, let me erase this. So compound R, we have 1, 2, 3, 4, and then we have a double bond here, right? As a result of removing bromo and H from the compound that result from reaction 2. So hydrogen, we need another one there, So let me just count to make sure that my things are in order. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. So that is organic compound R. And then we add HBr. Okay, when we add HBr, what are we gonna get? We're gonna get 1, 2, 3, 4, 5. So hydrogen. Now we need to use Markovnikov's rule. To determine where the hydrogen is gonna go and where the bromine is gonna go. So where is the hydrogen gonna go? The hydrogen is gonna go to the carbon with the most number of hydrogens. That is the Markovnikov's rule. So here we're gonna have 1, 2. The double bond breaks and the other hydrogen comes here. We have a hydrogen here. Now we're gonna have Br. So right, that is how we decide where the hydrogen is gonna go and where the bromine is gonna go. The hydrogen is gonna go to the carbon with the most number of hydrogens already, and then the bromine is gonna go to the carbon with the least. Okay, so this here is a major product. Yeah, if you swap H and Br, you have the minor product. Don't ask me whether you're gonna get it right or not. If you do that, please don't. So that is 4.6.1. 4.6.2, the balance equation for reaction 5 using structural formula and the correct reagent shown above. So for reaction 5, it means that we have to start with this compound in reaction 5 because that is the product of reaction 4. So in reaction 5, we start with, let me just copy the organic compound and proceed from there. So duplicate, and there we go. What are we adding? We are adding NaOH, and then what will be the product? Okay, so we're gonna have 1, 2, 3, 4. We need a double bond there. You're gonna see where everything else goes. So hydrogen, 1, 2, 3, 4. Okay, and then hydrogen. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I don't want to make any mistakes here with regards to the number of hydrogens. I want to make sure that everything is good. So we're gonna have plus, and then we are removing bromo and hydrogen, right? So we're gonna have NaBr plus H2O as our two products. Okay, but I'm having a concern now. There's something I'm thinking about. Let me show you why I'm saying that. So compounds R and T are positional isomers. Compounds R and T are positional isomers. So, okay, this is compound T. This is compound T, right? This is compound T. And then this here is compound R. So compound T is this product that we have here. And then compound R. Yes, compound R. This is compound R. Okay. So compound T and compound R should be positional isomers. But if you look at what I have here, they look the same, right? And that can't be. They're said to be positional isomers. They're not said to be the same compound. So we need to change the position of the functional group. But in compound R, we cannot really change the position of the double bond. It has to be there. It has to be here on these two carbons, or on the first carbon, because the Br is here, right? We don't have any other option with regards to compound R. But with compound T, we have a bit of flexibility. So we cannot have the double bond there, because if we have the double bond there, T and R are no longer positional isomers. They're just the same thing. So we must actually have the double bond here on the second carbon, right? Of which I don't see an issue why that cannot be the case. So how many hydrogens? 1, 2, 3. Oh, how many bonds? 1, 2, 3, 4. And here we have 1, 2, 3, 4. Here we have 1, 2, 3, 4. I'm just trying to make sure that I'm not making any mistakes. Okay, let me take a look at the molecular formula. 1, 2, 3, 4. So C4, and then 1, 2, 3, 4, 5, 6, 7, 8. H8. 1, 2, 3, 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. And here 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. The molecular formula 1, 2, 3, 4. So C4 1, 2, 3, 4, 5, 6, 7, 8. H8. Right, with the same molecular formula but different structural formulas. So I'm happy with that. And then 4.6.3, we are looking for the IUPAC name of compound T. So compound T, which is what we have here, will be we don't have any other we don't have a branch, so I don't need to worry much. We're gonna have build 1, 2, build 2 in. I will let you define the term reaction rate, and then we'll take a look at 5.1.2 together. So let's go through the question statement. The reaction between pure aluminium and excess hydrochloric acid is used to investigate the factors that affect the rate of reaction. So we have 2Al plus 6HCl to give us 2AlCl3 plus 3H2. Let's hear the stories. In this reaction, 1 mole per decimeter cube of HCl solution reacts with 0.5 grams of aluminium strip from an aluminium roll at room temperature. Okay, the graph of volume of H2 versus time for this experiment, not drawn to scale, is shown below, as you can clearly see. And then 5.1.2, actually let me write 5.1.2 up here. 5.1.2. For the time interval t is equals to 0 to t is equals to 5 minutes, the average rate for the formation of H2 is 0.033 decimeter cube per minute. Calculate the mass of aluminium present in the container at t is equals to 5 minutes. Take the molar gas volume as 24.5 decimeter cube per mole. Okay, so let's take a look at what is happening. We are looking for the mass of aluminium that is left at t is equals to 5 minutes. What are we given? We are given the rate of reaction of H2, which is said to be 0.033 decimeter cube per minute. The HCl is in excess, so we don't have to worry about that. We can, let that one go. And then what else do we have? We have the time, obviously, for the rate of reaction, which is 5 minutes. right? So we want the mass of aluminium that remains at T is equals to 5. So these are the steps that we're going to take. If we take the rate of reaction of H2 and say that it is equals to, so here the way we set up of our equation is decided by the unit we're given. We have decimeter cube per minute. So our rate of reaction of H2 should be the change in the volume divided by the change in time, because our SI unit is decimeter cube per minute, right? This change in volume that we are going to find, don't forget we're given the molar gas volume, right? So that change in volume will allow us to find the number of moles of H2. When we find the number of moles of H2, we are going to find the number of moles of Al that reacted. And from those number of moles, we're going to find the mass of aluminium. And then when we have the mass, we can then subtract it from 0.5 in order to find that which remains. So if in your calculation you don't subtract at some point of time, you didn't do it the correct way. There's some marks that you're going to lose. But either way, let's carry on. The rate of reaction is 0.033. This is equals to volume final minus volume initial, right? But the initial volume is 0. So we just have VF minus VI. VF for the volume, not the velocity. Okay, and the time is 5 minutes, which we can leave it like that because our SI unit is in decimeter cube per minute. So our final volume of H2 will be equals to 0.033 multiplied by 5, which is equals to 0.165 decimeter cube. So this is our volume. We can go ahead and find the number of moles. We will say 0.165 divided by 24.5. So divided by 24.5. This is equals to 0.06735. These are the number of moles of H2. Right, so we want to use this number of moles of H2 to find the number of moles of aluminium. So we're going to say number of moles of H2 is to number of moles of aluminium. So let's find the balancing coefficient. So H2, the balancing coefficient is 3, and then the balancing coefficient of aluminium is 2, right? And then we have found the number of moles of H2 to be 0.00675, and then the number of moles of aluminium, we can put X there and solve for X. Okay, so let me just make sure that the balancing coefficient are right. That of H2 is 3, that of aluminium is 2. Okay, so I'm happy with that. So we're gonna have 3X being equals to 0.00675 multiplied by 2, which is 0.01347. 0.01347. Okay, that is correct. So X is equals to, so I divided that by 3, I get 0.00449 moles. These are the number of moles of aluminium. Okay, so we have the number of moles of aluminium. We can find the mass because we know that it is equals to number of moles multiplied by molar mass. So the number of moles 0.00449 multiplied by the molar mass. Yeah, it is just Al, not Al2 or anything. So I can just go to my periodic table. It looks to be 27 here, but let me just make sure, I'm writing the final exams. I don't want to make any silly mistakes. So aluminium, where is it? There it is. It is actually 27. Okay, so we have 27. So multiply by 27, and this is equals to 0.12 grams. So this is the mass of aluminium which is used. This is the mass of aluminium which is used. Okay, how do we know that that is the mass of aluminium that is used? Because it's the mass we get from the number of moles of H2 that are that are produced, okay, that are formed. So that is the mass used. So what is the equation saying? They calculate the mass of aluminium present. Okay, so the mass present will therefore be the mass you started with, 0.5, minus that which is used, 0.12. So 0.5 minus answer on my calculator, I get 0.38 grams. So that must be the mass of aluminium present in the container. Stories. Let's take a look at 5.1.3. Assume that the concentration of HCl stays constant for the duration of the reaction. Okay. Use the collision theory to explain the change in the reaction rate from T is equals to 0 to T is equals to 5. So what will happen from T is equals to 0 to T is equals to 5? Well, we expect the rate of reaction to actually drop, right? Because the number of moles of aluminium are getting used up. So that's what we're expecting. We're expecting our curve to start off very steep but become gentle as time goes, right? So how can we phrase that? That is for 4 marks. So as the reaction proceeds, I'm not going to write it down because it's a lot. So essentially, as the reaction proceeds, right, the number of moles of aluminium are getting used up. Yeah, when the number of moles of aluminium are getting used up, we have less number of moles, right? And then when we have less number of moles, clearly we're going to have less effective collisions per unit time. When we have less effective collisions per unit time, the rate of reaction actually increases, right? It becomes slower, essentially. So that is 5.1.3. We can phrase this answer in a couple of different ways, but essentially, the number of moles of aluminium are getting used up. So when they're getting used up, we have less effective collisions per unit time, and the rate of reaction is going to go down. That is 5.1.3. 5.1.4, experiment 1 is repeated using a 2 mole per decimeter cube HCl solution. What was the solution initially? The solution initially was 1 mole per decimeter cube. Now it goes up to 2 mole per decimeter cube. The question says, redraw the above graph. Non-numerical values need to be shown in your answer book and label the curve A. On the same set of axes, draw the curve that will be obtained from experiment 2. Label this curve as curve B. Okay, so this is quite an interesting question. Let me show you why I'm saying that. Okay, so this is our Y, this is our X, this is our X, right? Let me just forget about the X and the Y axis for the time being. I just want to show you something. Yeah, as people are arguing about question 2 and the name of the alkane, I want to add something to the equation. So let's say that this is our original graph B. Okay, oh, not B, but A. This is A. So here's a question for you. Here's a question we should go to the comment and talk about. So we're supposed to draw a graph, a curve, and name it B, right? When the concentration of HCl has been doubled from 1 mole per decimeter cube to 2 moles per decimeter cube. But the HCl is in excess. So is it really going to affect our rate of reaction? Or is it not going to affect the rate of reaction? It's in excess. So tell me. So we're gonna have 2 colors here. We're gonna have red. Let's start with red, right? Red, essentially, I'm drawing it on top of green. And I'm saying that red is B1, right? It's on top of green. And then I'm gonna have another yellow line, and the yellow line looks something like this. You can see that the rate of reaction increases and our reaction ends way sooner compared to curve A. So let's call this one B2. So there we go. 2 possible answers, B1 or B2. When we increase the concentration of a substance that is in excess, will it affect our rate of reaction? AKA, what is the correct answer for this question? Did you go with B1 or did you go with B2? Let's talk in the comments. 5.1.4. Let's take a look at 5.1.5. So experiment 3, Experiment 1 is repeated using 0.5 grams of pure powdered aluminum. Initially we're using a strip, and now it is powdered, right? And then the equation 5.1.5, how will the volume of H2 produced in experiment 2 in experiment 3 compared to that in experiment 1? Choose from greater than, less than, or equal to. Trick equation. It is going to be equal to. It is going to be equal to, because we still have the same mass, right? So what is going to differ is the time it will take for our reaction to complete. But at the end of the day, we should have the same amount of H2, right? In experiment 3, the reaction ends sooner compared to in experiment 1, because experiment 3 is powdered, more surface area, blah blah blah. So we expect it to complete sooner compared to experiment 1. But ultimately, the amount of H2 produced should be equal to, right? So curve X is a Maxwell-Boltzmann distribution curve for a reaction under a set of reaction conditions. A change was made to one of the reaction conditions to obtain curve Y. So this is X initially, and then we change some conditions, get Y. Okay, what change was made to obtain curve Y? What change was made to obtain curve Y? We know fully well that this change, when the peak goes down and it shifts to the left, is a characteristic of what happens when you increase the temperature. So that is the answer to 5.2.1 and 5.2.2. There we go. Don't forget 5.1.4. Are you going with B1 or are you going with B2? Let me know in the comments. Define the term chemical equilibrium. I'm actually not reading the question, but telling you to define the term chemical equilibrium. That is 6.1.1. Let's take a look at 6.1.2. At T1, oxygen, O2, was added to the container. Write down the letter that represents O2. Choose from X, Y, or Z. Let's go through the question statement and see what is happening. So the reaction of carbon monoxide gas, CO, with oxygen gas, O2, is investigated. The reaction reaches equilibrium in a closed container at constant temperature T degrees Celsius, according to the balanced equation below, as we can clearly see here given to us. Changes to the conditions of equilibrium are made at different times. The graph shows the results obtained, X, Y, and Z. That represents the gases in the above reaction. Back to our equation. At T1, oxygen O2 was added to the container, rather than the letter that represents O2. So when we look at our reaction here, X, Y, Z, it should be easy to see that Z is what is added at T1, right? So that answers our question 6.1.2. We're supposed to write down the letter that represents O2 from X, Y, or Z. So the answer to 6.1.2, we have X. That is the letter that represents O2. Yeah, clearly there is a spike with regards to X at T1. So clearly it is oxygen, because that was what is added at T1, we are told. We're not supposed to give a reason, but I've sort of told you why that is. 6.1.3. At T2, the pressure is adjusted by changing the volume of the container. Was the pressure increased or decreased? How many marks? 1. Okay, I wish it was 2 or 3, because we really have to think. Well, 6.1.46 we must explain, so I guess the 1 mark is justified. So let's take a look at T2. At T2, X goes down, right? So O2 goes down at T2. And then we have one other substance, Y, that goes down, and Z that goes up. Okay, so we are told that the change that was made is with regards to pressure, right? So let's take a look at our reaction. On the right hand side, we have 2 plus, let me use something lighter. We have 2, okay, that is even worse. What is happening? We have 2 plus 1 moles of oxygen on the right hand side, right? You have 3 moles of oxygen on the right hand side, and then on the left hand side we have 2. Okay, why are we doing this? We want to sort of see how our reaction will react, how our system will react to a disturbance, because the system wants to oppose the disturbance, right? So what happened to O2? O2 at T2, it went down. Okay, so we're saying that the concentration of O2 goes down, okay? And then look at Y. Y also goes down. But after Y goes down, it doesn't bounce right up, because if you take a look at O2, O2 bounces up after it goes down. And then Y goes down, but keeps on going down. And then Z goes down, but bounces up together with O2, right? So because the changes with regards to pressure, we can say that O2, it's X, and Z is actually carbon monoxide. Z has to be carbon monoxide, so this is CO, and then Y should be carbon dioxide, CO2. So okay, O2 did go down, but ultimately it went up. So let's change that. O2 actually goes up ultimately, because when the pressure is changed, right, they all go down. Now we can conclude and say that the pressure was decreased here. How do we know that the pressure was decreased? The pressure was decreased because the rate of reaction, the concentration of all the reactants went down momentarily, as we can clearly see here. So O2 goes down for a moment, and then it goes up. Carbon monoxide goes down for a moment, and then it goes up, as we can clearly see in the diagram that we're given, right? But CO2 goes down and stays there. It goes down and stays there. So the pressure was decreased here, right? And then as the pressure was decreased, reverse reaction was favored. Reverse reaction was favored. Reverse reaction is favored because it is the one that leads to more number of moles of gas, hence increasing the pressure. So what is our question again? Was the pressure increased or decreased? The pressure was decreased. The pressure was decreased. 6.1.4. Why are we saying that the pressure was decreased? Reverse reaction was favored. Well, I'm not going to write. Let me just tell you. Reverse reaction was favored. And then reverse reaction, when it is favored, it leads to more number of moles of gas, hence increasing the pressure. The only way our system would react in this manner, where it leads to more number of moles of gas where the pressure is increased, is if there was a decrease in the pressure, right? So that is the answer to 6.1, 6.1.3 and 6.1.4, right? They look like they all go down momentarily, but you have to see beyond that and see, oh, okay, well, O2 ended up going up, CO ended up going up, and then it is CO2 that goes down ultimately. So reverse reaction has to be favored. Pressure has to have been decreased, because the reverse reaction leads to more number of moles of gas, hence increasing the pressure. Okay, 6.1.5. Let's take a look at that one. Write down the letter or formula of the gas that is represented by the letter Z. We already have the answer. 6.1.6. Give a reason for the answer to question 3.1.5. Well, can I say we already have the answer? You know, can I say that we already have the answer? We already have the answer. Why am I saying that we already have the answer? We can see that when the pressure was decreased, the concentration of the reactants goes up, right? And we can see that concentration of X went up, which we know to be oxygen gas, and concentration of Z went up. It has to be carbon monoxide, because that's the other reactants that we have. So write down the name of formula of letter Z, CO, carbon monoxide. You have the freedom of choice there. So that is 6.1.6. 6.1.7. What change in temperature is made at T is equals to 3? Choose between increase or decrease. T is equals to 3. So at T is equals to 3, O2 goes down. Carbon monoxide goes down. What does that mean? Forward reaction is favored, right? CO2 goes up, we can see. So forward reaction is favored. Let's go to our reaction and see whether our reaction is exothermic or endothermic. The forward reaction is exothermic, right? Forward reaction is favored. So it is the exothermic reaction that is favored, right? So which change in temperature favors exothermic reaction? Well, let's think. Endothermic absorbs heat, right? So if you increase temperature, endothermic is going to be favored so that it can absorb some of that heat, mitigating, right? And then if exothermic is favored, it means that temperature was reduced, and exothermic is favored so that it can release energy and the temperature can increase. So what change was made to the temperature at T3? If exothermic is favored, temperature was decreased, and if temperature is decreased, exothermic must be favored so that the temperature increases, because exothermic releases energy. That is 6.1.7, and we've answered 6.1.8. Use Lee-Chartgall's principle to explain the answer to 6.1.7. And now the elephant in the room, 6.2. Carbon monoxide reacts with water, H2O, at 2 degrees Celsius. The reaction reaches equilibrium according to the balance equation. We have carbon monoxide plus H2O to give us CO2 plus H2O. And then we're given the initial number of moles of carbon monoxide, of H2O, of carbon dioxide, and of hydrogen gas. And then we're given the volume, which is 2 decimeter cube. How often do we find the volume of 2 decimeter cube? It's like it's an examiner's favorite, this volume of 2 decimeter cube. But anyway, stories. If the equilibrium constant Kc for this reaction at 2 degrees Celsius is 4, calculate the mass of carbon monoxide present in the flask at equilibrium. Okay, so let's go ahead and have our table, right? So yeah, obviously you can answer the question in the absence of a table, you know, but for the faint-hearted ones, me included in this case, let's use a table. Yeah, it's quite hectic when we don't have a table. Yeah, it's quite hectic when we don't have a table. Yeah, but it's doable. It's doable. I've been convinced that we can do it without a table, but I still prefer a table. Okay, so this is carbon monoxide, this is H2O, this is CO2, and then this is H2. The balancing coefficients, we have 1, 1, 1, 1, so we don't have to worry about that. And then here I'm going to put my initial number of moles. Here I'm going to put the change. Here I'm going to put the number of moles at equilibrium. Here I'm going to put the concentration at equilibrium. So the number of carbon monoxide that I start with is 0.6. H2O 0.6. Carbon dioxide 0.1. H2 0.1. Our Kc is greater than 1. Right? Our Kc is greater than 1. It is 4 actually. Way greater than 1. So the forward reaction needs to have been favored in order for the Kc to be close to 4. That is the first thing that we have to see, right? So what will be the change? With respect to the balancing coefficient, here we can have minus x, because the reactions, they're going down, they're getting used up. And then the products, we have plus x. So at equilibrium, we're going to have 0.6 minus x, 0.6 minus x, 0.1 plus x, 0.1 plus x. And then the concentration, we just divide by the volume. 0.6 minus x over 2, 0.6 minus x over 2, 0.1 plus x over 2, 0.1 plus x over 2. So Kc is equals to concentration of CO2 multiplied by the concentration of H2. Everything divided by concentration of carbon monoxide multiplied by the concentration of H2O. So what is the Kc? The Kc is 4. Concentration of CO2, that is 0.1 plus x over 2. And then H2, 0.1 plus x over 2. Everything divided by concentration of carbon monoxide, 0.6 minus x over 2, 0.6 minus x over 2. So let's solve for x. First thing first, 4 is equals to 0.1 plus x over 2 to the power 2, because they are multiplying each other, right? Divided by 0.6 minus x over 2, everything to the power 2. We can take square roots on both sides. I'm not going to write it down, but hopefully you can see that. You can see the consequence of taking square roots on both sides here. We will have 2 is equals to 0.1 plus x over 2, right? Everything divided by 0.6 minus x over 2. So 2 is equals to 0.1 plus x over 2 multiplied by 2 over 0.6 minus x. 2 and 2 cancels out. 2 is equals to 0.1 plus x over 0.6 minus x. So 1.2 minus 2x is equals to 0.1 plus x. So 1.2 minus 0.1, 1.1. Okay, I feel so stupid, but I don't want to make any mistakes. X plus 2x is equals to 3x. So x is equals to 1.1 divided by 3, which is 0.3667. What are we looking for again? The mass of carbon monoxide at equilibrium. So number of moles of carbon monoxide at equilibrium. Let's go to our table. Carbon monoxide at equilibrium, we have 0.6 minus x, is that right? So this is 0.6 minus 0.3667. Let me put that in my calculator. I get number of moles being equals to 0.2333 moles. So the number of the mass rather is equals to the number of moles multiplied by the molar mass. So we have 0.2333 molar mass of carbon monoxide. I think just 12 plus 16. So multiplied by 12 plus 16. This is 6.53. So 6.53 grams is equals to well, that's the mass of carbon monoxide at equilibrium. There we go. Let's keep 7.1 and go straight to 7.2. Why am I saying we must keep 7.1? I don't want to break a lot of hearts. A lot of people got 7.1 wrong. There's a word that they miss at the end of the definition. So I don't want all that smoke. Let's just keep 7.1 and go to 7.2. So write down the formula of the conjugate acid of the carbonate ion 7.2 CO3 to the 2 minus. Well, we can answer this question without any context, but let's just take a look at the question statement. Hydrated potassium carbonate K2CO3 H2O is a weak base. A solution is prepared by dissolving some of this solid in water. So what is the conjugate acid, right? It is the ion that is formed when these bases accept a hydrogen, right? So the answer to 7.2 is HCO3 to the minus, right? No longer to the 2 minus, but just to the minus, because we have accepted a hydrogen. So, well, we have accepted a hydrogen plus we have accepted a proton. So it must be to the minus and not to the 2 minus. Hope you didn't make that mistake. 7.2. Okay, let's hear the stories. In 7.3, a hydrochloric acid solution HCl of concentration 0.1 mole per decimeter cube is titrated with the prepared potassium carbonate solution of unknown concentration. The balance equation for the reaction is K2CO3 plus 2HCl to give us, 2KCl plus CO2 plus H2O. And then the equations 7.3.1 determine the value of P. Okay, so let's take a look at what happens. We have two runs. In run 1 and 2, the volume of HCl used is the same, right? 25 centimeter cube. Okay, and then in run 1, where we find P, we are given the initial burette reading of K2CO3. It is 6.5. And then the final reading of the burette is P, which is unknown, right? And the volume of K2CO3 that is used is 20.05. And we are looking for the value of P. Well, this is how a burette looks like, right? Let me just put a sketch real quick, and so the readings on a burette, they start low, and as you go down they get high. So here you will find something like 5, 10, 20, 25. This is how the readings on a burette look like. So the final reading will always be greater than the initial reading in a burette, right? Because the numbers, they increase as you go down. So the volume of K2CO3 used is 20.05 in run 1, right? And the initial reading on the burette was 6.5. So the initial reading was somewhere here, 6.5. And we know that 20.05 is used. So what should be the final reading if 20.05 is used? Well, we just say that P is equals to 6.5 plus 20.05. So let me just put that in my calculator. 6.5 plus 20.05. I'm getting 26.55. So the final reading, so the initial was somewhere here, 6.5, and then the final reading was somewhere here, 26.55. This is the initial reading, and then this is the final reading on the burette, because the numbers go up as you go down. So this is the answer to question 7.3.1. that is the value of P. Okay, and then 7.3.2, we're looking for the value of Q. So Q, which we have here, is the initial reading, right? So how are we going to find the Q? We're just going to see the volume, the final reading, which is 48.3 minus the volume that is used, 20.15. So 48.3 minus 20.15, this is 28.15. Yes, so Q is equals to 28.15. That is the value of Q. That is the value of P. Okay, and then 7.4, methyl orange is used as the indicator. Explain why methyl orange is most suitable indicator for this titration by referring to the pH at the equivalence point. Okay, so we need to break down this reaction that we have, right? We have K2CO3 and HCl. So K2CO3, if we are to use methyl orange, should be a weak base, right? So we have a weak base plus a strong acid. The equivalence point when we have a weak acid and a weak base and a strong acid, the pH should be less than 7 at the equivalence point, right? Around about 3 to 5. This should be the range of the pH at the equivalence point. And we know that methyl orange changes color along that range. That's why we use it to determine the equivalence point when we have such a reaction between a weak base and a strong acid. Okay, and then 7.5, for 5 marks we are supposed to calculate the concentration of K2CO3. So I wonder what information we have, but let's take a look. So we have K2CO3 plus HCl. So this is what we're dealing with. We're supposed to use these two to somehow find the concentration of K2CO3. Okay, so let's take a look. So obviously we want the concentration of K2CO3. So already that tells me that I need to somehow use information that I have with regards to HCl, and use that information to find something with regards to K2CO3, because chemistry essentially, right, it's about using what you have to calculate what you don't. So let's see how we can do that. Let's see the information that we have. We have the concentration of HCl. So the concentration of HCl is said to be, so C is equals to 0.1 mole per decimeter cube. And then what about the volume of HCl? So we can use, oh, well, it is given to us as 25 centimeter cube. So 25 centimeter cube. So already looking at these variables, I can find the number of moles of acid, right, HCl. With the number of moles of acid, use balancing coefficients, find the number of moles of base. With the number of moles of base, I just need the volume of the base to therefore find the concentration of K2CO3. Okay, so which volume of K2CO3 am I gonna use? We have 20.05 in run 1, and then in run 2 we have 20.15. So which one do we pick between these two? Which one are we gonna use? A bit tricky really. But I think we have three options here. I think we can use run 1, that would be fine. And then we can use run 2, and that should also be fine. Yeah, because the volume of HCl used is the same. So if the volume of HCl used was different, then we were gonna use it as a coordinate. Take the volume of HCl and its corresponding volume of K2CO3. But here we have two different volumes. Or better, we can add the two volumes and divide by 2 and use the average volume. All right, I think that will also be fine. I think we have that freedom of choice. Okay, so let's go. We're gonna add the two volumes and we're gonna use the average. So the number of moles of HCl CV, so we have 0.1 25 over 1000. So let me put that in my calculator. So 0.1 multiplied by 25 over 1000. I'm getting 0.0025 moles. This is the number of moles of acid. Let's check the balancing coefficients. We have 1:2, right? So we can say that the number of moles of acid is to the number of moles of base. We have 2:1. So that of acid is 0.0025. We can just divide that by 2 to find that of base. So we have 0.00125. This is the number of moles of base. So we have the number of moles of base. We are looking for the concentration. Volume, we said that we're going to add the 2 and divide by 2. So 20.05 plus 20.15 divided by 2, 20.1. So I'm going to use a volume of 20.1. I'm going to find the average of the two. So the concentration, the number of moles over volume, number of moles is 0.00125, and the volume is 20.1 divided by 1000. So I can just multiply with 10 to the minus 3. So 0.00125 divided by 20.1 times 10 to the minus 3. I'm getting 0.062 moles per decimeter cube. This is the the concentration of K2CO3 that I end up with. Okay, and then now let's go to 7.6. Right. So the value of x. So we're going to do 7.6. After 7.6, after question 7, really, we should do question 8, 9, and then we go to question 1 and do the multiple choice. But it's gonna depend on the value of x that I get. When I calculate the x, I want a whole number, right? If I don't get a whole number, we're done. Yeah, so if you want to watch me do question 8, 9, and 1, hope that we get a whole number, because if we don't get a whole number for the value of x, I'm not gonna think that the question is wrong. I'm gonna think that I am wrong, and we're gonna call it quits. So let's see. The above K2CO3 solution is used. The above K2CO3 solution used in the titration was prepared by completely dissolving. So we have a mass there of the hydrated potassium carbonate, 6.525 grams, in 600 centimeter cube of water. And then the question says calculate the value of x in the formula. So, okay, this is what I'm thinking. So the volume that this mess was dissolved in is 600 centimeter cube, right? But the volume that was used, I don't even know how to name these things. So this is the volume that was used to prepare. And then the volume used, if you look at run 1 and, oh, well, am I looking at the right thing? No, I'm not supposed to look at run 1. Yes, I am supposed to look at run 1, but not ACL. I'm supposed to look at K2CO3. Yeah, if you look at the volume of K2CO3 used in run 1, it is 20.05. And then in run 2, it is 20.15. So let's carry on using the average, right? The volume used is 20.1 centimeter cube. And what number of moles were present in this 20.1 centimeter cube? Let's find out. We had 0.00125 number of moles present in a volume of 20.1 centimeter cube. So the number of moles here is 0.00125 moles. Yeah, so these are the number of moles present in 20.1 centimeter cube. But we know that this mass was dissolved in 600 centimeter cube. So what is the number of moles present in 600 centimeter cube, right? That's the question I'm asking myself. How am I going to find that? I'm going to say number of moles in 600 centimeter cube should be equals to 0.00125, the number of moles in 20.1 centimeter cube, right? Multiplied by 600 divided by 20.1, because these are the number of moles in 20.1 centimeter cube. But we know that the mass was originally dissolved in 600 centimeter cube. So how many number of moles are present in the 600 centimeter cube? That's what we are trying to find here. So this is going to be equals to, so let me just put that in my calculator. 0.00125 multiplied by 600 divided by 20.1. I'm getting 0.03731. Let me just look at my substitution once more and see that I've not done anything wrong. So this is 0.00125 is fine. And then 600 divided by 20.1, 0.03731 moles. Okay, so these are the number of moles when we dissolve 6.525 grams of the hydrated potassium carbonate in 600 centimeter cube of water. Okay, so we have the number of moles, we have the mass, we can find the molar mass. This is how I want to find X. So I'm going to say that number of moles is equals to mass divided by molar mass. The number of moles that we find in 600 centimeter cube, it's 0.03731. The mass used is 6.525. So here, in place of molar mass, it's where the X is going to come in play, and we will try and find it. So let me take my periodic table. K, where is K? Potassium 39, right? So okay, I'm just going to put this in my calculator and write one well. So 39 multiplied by 2, right? I'm putting K2CO3, and then I'm gonna say plus, and then put X multiplied by the molar mass of H2O. Okay, carbon K2CO3, carbon is 12, oxygen is 16, we multiply by 3, we get 138. So I have 138 plus X multiplied by the molar mass of H2O. So H2O 1 multiplied by 2 plus 16, 18. So 18x, let's just write this as 18x. Okay, so now the problem becomes mathematical. 0.03731 multiplied by 138. So I'm getting 5.14878 plus 0.03731 multiplied by 18x plus 0.67158x is equals to 6.525. So obviously I'm gonna take this to the left hand side. So 6.525 minus, is this 5? Is this 5? Is this 5? Okay, let me multiply 138 with 0.03731 again. 5.1485. So this is 5. Yeah, I think I don't want to get to the final answer. I'm taking as long as I can because I don't want to get to the final answer. Yeah, this question is really freaking me out. So 6.525 minus 5.14878. So 0.67158x is equals to, I press answer, I get 1.37622. So x is equals to 1.37622 divided by 0.67158. I'm having a lot of fun, to be honest. So I just need to put this in my calculator. I'm not sure I want to. Because if this answer is not a whole number, I'm not carrying on. Okay, moment of truth. I get 2.005. I get 2.05. So can we say that x is equals to 2? Can you say that? Yeah, maybe because I'm not rounding off here, that's why I'm not getting exactly 2. But there we go. X is equals to 2. When I do this, when I use this approach, this is the answer that I'm getting. Yeah. So let me know in the comments, which approach did you use and which answer did you get? And when you're taking a look at my approach, can you tell me where I am lying? Right? Yeah, because I can sort of justify what I'm writing, but maybe there's an assumption that I'm making which is not necessarily true. So let me know in the comments, where am I lying here? Where am I lying? Do you get the same answer? If not, what answer do you get? Here we go.